We are continuing our discussion about confidence intervals by building confidence intervals for proportions. So we're looking here at population proportions. Sometimes we're interested in knowing the percentage of subjects that fall within a certain characteristic of interest. So for example, we could be looking at the percentage of first marriages that end in divorce. And we might have that our sample proportion is 43%. That would be our sample statistic, that's p hat. And we want to make inference about the greater population, what percentage of first marriages end in divorce, not just for our sample, but for all first marriages. And so we want to extrapolate from our sample statistic to find a population parameter. A point estimate would be to say that sample proportion, that 43%, is an estimate of the greater population. But we also recognize that a sample statistic is a random variable and it has a sampling distribution. So when you take different samples, you get different percentages. And so because of this, we want to give a range, an upper and a lower bound for that population proportion. So we're going to look at how we do this. Now, population proportions are used when we have categorical data, so nominal variables. It could be things like the fact that you are married or not married, divorced or not divorced, but it can also be like preferred presidential candidates. So in the US, we have two parties, Republican, Democrat, and so we could look at percentage who vote a Democrat, for example. Or we could look at percentages who watch the presidential debate. So our sample could be that 1 out of 6 people watch the presidential debate. Can we extrapolate that to the greater population's viewing habits? So it needs to be categories where we can look at, did they fall in this category or not in this category? So voted Democrat or didn't vote Democrat. That they are divorced or not divorced. They watched the show, they didn't watch the show. Okay? So we're trying to extrapolate to the greater population. When it comes to proportions, right, our proportions is a fraction or a ratio, and we calculate that proportion as the number of occurrences divided by the size of the sample. So of the people who were sampled, how many of them were divorced? Of the people sampled, how many watched the presidential debate? So X is the number in a particular group or category, and N is the total number of items sampled. When it comes to the sampling distribution for proportions, we've talked about this previously, the expected value of the proportion. So if we think about, remember the average of the averages was the population average. Well, when it comes to proportions, the average of all the different proportions from the samples is the estimate of the population parameter proportion. So the expected value of p hat is p. The mean of all of the sample proportions gives us the population proportion. The standard deviation, the variability in the sampling distribution when it comes to proportions, is the square root of p times 1 minus p over n. And we've looked at this previously. So we looked at z-scores for proportions. We looked at how z equals p hat minus p divided by the square root of p times 1 minus p over n. The challenge we have is we can't easily rearrange the equation to solve for the parameter p. Therefore, we're going to have to use just a close approximation of this formula where essentially we are replacing the proportions here for the variability with the sample proportions. So notice that this is the true one, but the problem is that unlike before we rearranged the formula and solved for mu, we can't easily rearrange the formula and solve for p because there's a bunch of p's everywhere. So we're going to solve for p, but we're going to replace those bottom ones with p hat. So what do I mean by that? We are basically going to take this formula here and rearrange it to solve for p so we can get a lower bound and an upper bound that we can be confident about. So notice how you can't rearrange the original one with the p here and the p's there. So how does this work? Well, with the confidence intervals for means, right, we used a z-score, and we then found the z's for whatever level of confidence that we want. Well, when it comes to proportions, we can use the same z distribution as we had with our means. So you'll see here this z or z, alpha divided by 2, that's going to be that same z that we looked at before. Recall, and I'm just going to quickly go way back. So my apologies for all this scrolling. So you'll remember our discussion here. We came up with the z for 95% confidence, 90% confidence, and 99% confidence at 1.64, 1.96, and 2.58. You're going to use those exact same numbers for your proportions test. 1.64 for 90%, 1.96 for 95, and 2.58 for 99. Ooh. Go through all these here. There we were. Okay. So we're going to use those Z's for our confidence intervals. So that means then, just like with before, we have our point estimate. And our point estimate, we're going to approximate the population parameter using the sample statistic. So our point estimate is the sample proportion. And then we do plus or minus the margin of error. And the margin of error here is going to be z alpha divided by 2 times the square root. And here we have p hat 1 minus p hat divided by n. That will give us our upper and our lower bounds. So let's take a look at that. But first, the assumptions for proportions are 3. We have a random sample, so we can never really make inferences about the population unless our sample is a proportional sample, is random. So it represents the population in terms of its variability. The other thing that we have here with proportions is that we have a binomial distribution. So we look at the nature of what we're measuring and the fact that we are measuring success or failure. So you're a Democrat or you're not a Democrat. You watched the TV show or you didn't watch the TV show. You are divorced or you're not divorced. There are 2 options there. The other keys for the binomial distribution is that if we grab someone at random and we look at divorce, not divorce, the probability they're divorced is not dependent on who we picked previously for our sample. So that population is sufficiently large that if we pull someone at random, that probability that they are in that category we're classifying as success is independent of the probability the next person is in that category that we're quantifying as a success. So independent trials, counting the number of successes, that's a binomial distribution. And we have to have it in terms of success and failure. So 2 categories, you're in it or you're not in it. The other thing is that we want to have our binomial distribution have sufficiently large sample size in order to approximate the normal distribution, to use that z-score. So that's why the check here. This n times the probability in the sample must be greater than 10, and n times 1 minus the probability in the sample must be greater than 10. That is checking that the sample size is sufficiently large to give us that normal distribution. All right, so let's look at this problem. Let's look at how do we go about creating our confidence interval. So a market survey is conducted by your state legislator to determine the proportion of homeowners who would switch to a new electrical energy supplier if they had the opportunity afforded to them by new state legislation. Of the 1,200 homeowners surveyed, 800 said they would switch. So our p hat is 800 divided by 1,200. Our sample size is 1,200. The number of successes here is the number that said they would switch. And so we have 800 divided by 1,200. Our point estimate for the population proportion P is going to be P hat. So 800 divided by 1,200 is going to be the point estimate. When we are looking at estimating the standard error of the proportion, we are looking at p hat, 1 minus p hat, divided by, so this is the point estimate, standard error. Standard error, remember, is the variability of the sampling distribution. And if you take your standard error and you multiply it times your z-score, you then get the margin of error. Okay, so just to clarify on wording here, point estimate, standard error is the variability in the sampling distribution. When you multiply standard error times the z-score, you get the margin of error. So we want to know the standard error. So p hat times 1 minus p hat divided by n, all square root. P hat 1 minus p hat divided by n, all square root, is going to be our standard error. Which in this case here is going to be our 800 divided by 1200 times 1 minus 800 divided by 1200 divided by 1200, all square root. Okay. And we construct a proportions confidence interval, and we can do that if all the assumptions are met. Well, what were the assumptions? A random sample. We had to have a binomial distribution, and we had to have n times p hat had to be greater than 10. Oops. Well, n is 1200. P hat is 800 divided by 1200. Those cancel out, and we end up with 800. So n times p hat is definitely more than 10. And you could check n times 1 minus p hat. Those are the ones who are not wanting to switch. And so in this case, that's going to be 1200 times 1 minus your 800 over 1200. So what we end up with there is that there are 400 who were not going to switch. Again, that is more than 10. We have a nice big sample size. We can assume that normality. So now we can construct a 99% confidence interval for the population proportion. Recall that in order to do a 99% confidence interval, we just need to find a place to write this. We're going to take our point estimate, p hat, plus or minus, we need a z alpha divided by 2, and we need the z alpha divided by 2 that goes with a 99% confidence interval, and then times p hat, 1 minus p hat divided by n. All right, let's do this by hand in Excel and in Python. Okay, so if we're doing this simply by hand, we need to know, first, we have p hat, 1100 divided by 1200. Here is our p hat, 800 divided by 1200, our 2/3. Okay, then what we need is we need our equals square root, and then this is going to be our p hat times 1 minus our p hat, and then we are going to divide that by n, and n here is 1200. Okay, so we have our p hat, we have our standard error, and we need also our z for when we have a 99% confidence interval. And so can you remember what that is? Right? It's 90% is 1.64, 95% is 1.96, and we have 99% is 2.58. Okay, so then we can find our margin of error is going to be standard error times our z-score. There's our margin of error. And our upper and lower bounds, it's going to be p hat minus our margin of error is the lower bound, and our p hat plus the margin of error is our upper bound. So here we've done it entirely by hand. We are saying that our population proportion is somewhere between 63% and 70% with our 99% confidence. If instead we want to do this confidence interval fully in Excel, we have a bit of a problem, because if you recall, when we do confidence interval, we can do norm or we can do t, but notice with the norm, it wants an alpha, a standard deviation, and a size. And we don't have a standard deviation. We do have, what are we doing, 99%. We do have our standard error here, size. What do we have here? Our sample size, 1200. Okay. So it doesn't quite work with what we want to do because it's used to finding confidence intervals for a mean, not for a proportion. What we can do is we can do these confidence intervals for proportions in Python. So let's do that. So just a reminder, if you didn't watch the previous video, that we're going to be starting to do a bunch of our stats in Python. That's because Excel is limited as you get to doing more advanced statistics. There are other types of statistical packages you could use, JMP, SAS, SPSS, R, Python. My particular favorites are R and Python because they are open source. They don't cost any money. And so in our videos, we're going to be using Python to do it. Partly because we can do Python just in our Google Docs. It's free, it's open source, and you don't have to install a whole bunch if you just do it in Google Colab. And then the other benefit is if you learn coding in Python, you can then use it for machine learning, AI, building apps, all kinds of stuff. So we might as well learn it so we can use it for lots of different things. If you are working along with us, you can find Python workbooks for anything that is in my videos on my site. And so right now we are going to drstephpowers.github.io/BIA. This is where you will find the workbooks that go with my book, Business Intelligence and Data Analytics Handbook. We are working here in the supplemental materials here called confidence intervals. If you click here in confidence intervals, then what you can do is click open in Colab. What that will do is it'll open a workbook for you. In order to edit and run this workbook, please go and save a copy to your Google Drive. So you need to be logged into your own Google Drive to have that copy. The other thing you'll want to do is to take, let's go back here, go into data on the left. And we are using the statistics and the statistics 2 Excel spreadsheets. If you click on them and you click this download button, which of course my face is covering up at the moment. So here's the download button right here. Then download it and then just drop that file into your Google Drive. So here's these 2 Excel spreadsheets that you can dump into your Google Drive. And so then what you will do is link to your Google Drive. So here I am, I have saved a copy into my drive and I am logged into my Google account with my copy of the workbook. And then what I'm going to do is I will import some packages that will allow me to manipulate and import the data. So we import pandas as PD, and this allows us to then import our Excel files that we'll do in just a moment. And then we import NumPy as NP. This package will allow us to manipulate our data, do things like drop cells that contain no information. So we import those packages to get us started. Then what we're going to do is we're going to take our own workbook here and link it to our own personal Google Drive. This allows your workbook that nobody else has access to work with your documents in your Google Drive. So this is only giving access to you and to your stuff. Okay, so you're not giving access to anybody else when you click on this. From Google Colab, import drive, drive.mount. When you do this, it will then create a pop-up that will ask you if it has permission to link this workbook, your copy of the workbook, to your Google Drive so that you can actually import documents. And so we are importing here using pandas. We are reading an Excel file called statistics.xlsx. And for me, that file I put into a folder in my Google Drive called the BA Handbook, and then in a folder in that called Appendix. So it's telling it where to go get this Excel file, and it's going to tell it what sheet name I want. So if I have a particular data set that I want from that, I will import it this way. Now, this is how to get the data from our previous example. What we're going to do right now is we are going to do a confidence interval for a proportion. Well, a confidence interval for a proportion doesn't require a list of raw data to analyze. We simply just need to know the number of occurrences out of our sample. So we don't actually need to import a data set for this particular problem. So this mounting of this Google Drive and this importing of the data, those two pieces you needed from our previous video. But for this particular video, all you really need is import pandas as PD, import numpy as NP. And we can do the rest from there. To do a proportions confidence interval in Python, what you do is you import statsmodels.stats.proportion, and to make life easier, let's just call it prop, something short, easy to remember. Which means then we can then call that package that we named prompt, and then from there we want the proportions confidence interval. The pieces to your proportions confidence interval are first, see if I get that to show back up, are the counts. So we had 800 people out of 1,200 people who fell into our category that we consider to be a success. So if I just go back to our original problem set, of the 1,200 homeowners, 800 said they would switch. So we have 800 out of 1,200 who said they would switch. 800, 1,200. Then we specify our alpha. And in this particular example, what are we doing? A 99% confidence interval. So if we're doing a 99% confidence interval, then our alpha is not going to be 0.05, but it's going to be 0.01. If it is a 95% confidence interval, alpha is 0.05. If it is a 90% confidence interval, alpha is 0.1. Here we're doing a 99%. And our method here is normal. We're using the normal distribution. So when we do this, we get a lower bound of 0.63 and an upper bound of 0.7. Let's compare that to what we came up with here, 0.63, 0.7. So you can see we've gotten the same confidence interval as we have in Excel with our line of code in Python. If you're doing this line of code for yourself with your own data set, you're going to import statsmodel.stats.proportions, give it a name, call proportions confidence interval. We have our count out of our sample size. This is a 99% confidence interval, and hit run. And then you'll get your upper and your lower bound. So we calculated it in both Python and Excel. Let's go back to our original question, which is it reasonable to say that 2/3 of homeowners would switch? Well, 2/3 is 0.67. Whether you're looking at the Python code, 0.67 is within that confidence interval. If you're looking at the Excel, 0.67 is within that confidence interval. So it is reasonable to say that 2/3 of the homeowners would switch. Now, what if when you're doing this, your n times p hat is less than 10? So you don't have a very large sample size. Well, then in that case, you can do what is called a continuity correction. A continuity correction is an adjustment to the z-score because the normal distribution is a continuous function and it's being used to approximate a discrete distribution, right? That binomial. So when n is small, you can adjust your z-score by doing this extra step here, which is this minus 1 over 2n. So that is a continuity correction. Another adjustment that you might need to make is that what if your trials are not independent? So if you need to do a finite population correction, this is an adjustment to the Z-score because the population is finite. What this means is that if we have a small population and we pull our sample from it, then we no longer have independent trials. So if I have a group and I am pulling out a person and saying, are you divorced? And then I pull out the next person and say, are you divorced? We're assuming that it's a big enough pool of people you're pulling your sample from. The probability of being divorced is the same for each person that you pull into your sample. But if it's a small population, so maybe there's only 10 people in total, when you pull one person out, then that means there's less people left in the pool who are divorced. And so the probability of pulling someone who's divorced is actually going to change depending on whether you pulled the first person as someone who's divorced or not. So when you have a small population, your trials are no longer independent. So then we have to do what's called a finite population correction, which is an adjustment to the Z-score when sampling is done without replacements, which is we're not throwing you back into the pool when we do the next random draw for somebody to be in the sample. A parameter can be more accurately estimated from a small population when a large portion of that population's units are sampled. And so the finite population correction is going to reduce the standard error in the formula because of this, because our sample is now a bigger part of the population. And so you can see the correction here, big N being the size of the population, little n being the size of the sample. So there's this additional correction here if your population is relatively small. With both of these finite population corrections and these continuity corrections, for confidence intervals, you'll have to do those by hand. When we look at hypothesis testing, the hypothesis tests do have some of these built in. When we're doing them in places like Python, it will have like the finite population corrections where you just toggle it on and off in that. So we'll get to that later when we get to some of the hypothesis tests.